not clear, just feel free. So yeah, I will start it. So for today, I want to sharing about toward privacy preserving audio understanding and speech processing. So although it's like the applications are on privacy, especially on speech, but the general idea is we will introduce some differential privacy basic at the first part of the talk. Right. So a little bit about myself. So I'm a PhD candidate at Georgia Tech at the Electrical and Computer Engineering department, and yeah, so I'm receiving the study abroad scholarship. So once I come back to Taiwan, I feel I should share some of my learning, and that's why I'm sharing for the privacy preserving part today. So my research interest is mainly on robust speech processing, sequence modeling, causal inference, and reinforcement learning. But for today, there are more about the speech processing part and coming from the privacy perspective. So yeah, I have some other experience. Like I was in EPFL as a summer intern in 2018 and meet Professor Huck there before he graduated. And I was in Alexa Speech and well-being research this summer. All right, so for today, we don't require any background on the privacy preserving, but we'll highlight why there is some new data usage issues related to differential privacy, and we'll give speech as the application cases. And more importantly, why privacy become more important in these 2 years, 2 to 3 years especially, is there's a new data protection regulation. So for example, GDPR and CCPA. But when we hear about this privacy protection regulation, we don't know why the connection between data protection regulation and the technical paper. So one major component is those new data protection regulations, they require some privacy measurements. So we'll have those kind of review. So even you are not coming from a technical background, you can still have some take with you. And we'll have some literature review, and finally will be some application when the differential privacy meets the deep learning algorithms. Right. So before started, like any data, like speech or faces, like speech especially, and its acoustic feature contain unique and rich personal information. For example, when we heard the voice from Morgan Freeman, you can know, the style, the speaking style, the accent is easy to figure out who is the speaker and the gender and those kind of information. But when we have a machine learning based application, for example, we want to recognize the face or we want to understand the text, mostly we don't require those of the identity-based information. But once we have a large-scale model, those sensitive information still somehow get learned by the model and somehow that our privacy has been leaked out with a large data-based model. So that's the motivation why privacy become a new topic and people start to look at it. So, for example, as a speech, when we talk to Siri, not just the sentence we want Siri to know, Siri also gather information like the speaker identity, who are you, and when you were speaking, like the indoor, outdoor, you speak in the living room or the bathroom, and some kind of the gender and those kind of ages information. And more importantly, when we talk about other applications like computer vision and text, we do the face recognition, we'll do verification or text recognition. Those information are more than a single task we want to reserve for a prediction task. And can we somehow preserving those sensitive information when we decide model become new interest, especially in recent years? And why there is a trade-off and why, like when we have large models and why these things become more and more sensitive? Because as far we know, model can have achieve high accuracy when require large set of training data, not just in speech, also in computer vision. When we want to train a large model, like a neural network-based model, they often have to collect a lot of data. So the training samples mostly are collected from the users, like the ImageNet or those kind of public data sets. It's like we don't really communicate with the data provider, but we just randomly searching from the internet. But mostly they will contain some personal information. Like, imagine you are a data provider just randomly sharing a voice or an image on the internet, but when your voice or your face data has been used to train a large model, so do you have the authority of the model, or how much like the model give the feedback to you once those kind of model has been created and used in different applications? So another question would be, okay, we know that they should possibly have some security threat against user information protection, but well, what could be the real data leakage cases? So there's two major cases from the data leakage perspective. The first demonstration called the model inversion attack. That means once you have created a neural network model, you can try to recover some training data which has been used to train the model. For example, if I use these faces to train the neural network model for first face verification, so you can use model inversion attack to find some like random pixel which have the maximize likelihood and to have the verification to its original face. And gradually you can find a face similar to its training sample. But here I have to say it's a special cases because they don't really refine some others label, but there's a demonstration showing by some inversion you can recover this high confidence data similar to its training sample. Meanwhile, there is another attack called the membership inference. That means we want to know whether a certain user has been using the model or not. For example, if I go to hospital, I don't want to let all the people know I have this visit to a specific hospital. But with the membership inference, they can retrieve whether data in the training set or not. So they can have this binary information and then use this MATLAB classifier to further inference the well-trained model. So those cases showing, okay, there's indeed some special cases when the large model has been created, and then they indeed have some data leakage meanwhile. But when we have new technology, they always have some new threats. But why is the real power behind to motivate us to design those new privacy-preserving algorithms? So there is some interest from the public regulations. So two public regulations, especially called the Data Protection Regulation, has been created pretty recently. The first one is European Union General Data Protection Regulation, so-called the GDPR. So when people all talk about GDPR, it's important, but they don't talk about why they relate to privacy. So here I got two concrete cases why they require this kind of privacy protection. So first, in the Article 4 of the GDPR, they clearly state we should have some privacy measure and protection. But protection is kind of a big word, right? So you can create a system and do some encryption like the people doing previously for decades. But why does it make privacy measurement is something we want to share during this short talk today. Another thing is we have to limit the access using custom data. For example, if we have a federal architecture or decentralized architecture, we have isolated training data, and these things have been stated in the Article 15 of the GDPR. So these things actually have been discussed in 2016. It's just before the ImageNet boom, but certainly they have become effective in the 2018. And I have really impressive memories. I was in ICML in 2018, and the people talk about, okay, GDPR has been implemented and why people should be worried about, and we should develop federal learning at that time. Meanwhile, after the regulation pioneer in the European countries, in United States, they also have a new data regulation pretty recently. They call the California Customer Privacy Act, CPA. So CPA also requires new stuff called the technical privacy measurement on the customer data. So there is some statement here. So the CCPA also has been effective in 2020. So for those big companies, they have to care about those stuff because California is where most of their headquarters are located. So let's spend some time to look at the GDPR before we look at the technical detail. So the idea of GDPR is to give control to individuals over their personal data. For example, when we're sharing those data on the internet, right? So we don't really think of those data will be used to create a large model. But once we also have authority of those data, so how to define the relationship between the data provider and the actual the company who collect this data to create a large model. When our data has been reused, how our personal information can be protected. So that is the Article 4 mainly talk about, and they further talk about these things in Article 15. So is there any cases when the GDPR has been implemented? So why is the real effect? So first effect is people do require some model parameter protection. For example, originally we all talk about the data protection, but since the model parameters actually train and create based on your individual data, so the model parameter also associate to those data provider. For example, if we use the Asian people to create a face recognition system, or use people from the other races, the parameter should be different and will be really depends on the data provider. So that is the shift when people talk about GDPR and create those accuracies. Meanwhile, they have some example of government in industry response. The first thing is Google actually have a 15 million GDPR fine on ADs and speech model because they don't do this kind of measurement. And I actually have a link about this GDPR fine, but since the computer, I couldn't open the table. But still for now, those European countries, and I heard that pretty recently, Taiwan also look at this issue and trying to have a similar regulation, and then the government will base on this regulation to have some fight. But meanwhile, in 2016, there's a special document from Apple. They use the differential privacy on their devices. So they call this privacy budget. So if you look at this official document of Apple or directly Google differential privacy and Apple, you can find a document saying they preserve some privacy with the privacy budget with absolute of 8. Okay, now we have a new term called the privacy budget and a new number called absolute of 8. But before really going to the technical detail, we know, okay, some people get rid of this refinement and then they define privacy budget to measure these privacy laws when we create a large-scale system. So before we go into further discussion, to empower high-performance speech processing or any kind of data central model, first, a large amount of customer data are required. Originally, they should be labeled data, but more recently, when we talk about the SASL model, a lot of even unlabeled data has been used to create those large-scale self-supervised model. So, but even those data without a label, they still associate some in the individual information. And meanwhile, the demonstration from the model inversion attack and the membership inference attack showing deep neural network-based model associated with severe privacy-related risk and concerns. And finally, a modern format of privacy measurement is required under those regulations. That's the motivation of today's talk. We are sharing about how we can refine these things by differential privacy and other technique, and finally we'll look at some. All right. So that means how to measure and protect privacy loss of speech data. That's one of the focus today, but the framework can be used on different kind of data. All right, so that should be the second part of the talk. Is here. So I want to say, because in general, privacy preserving machine learning or privacy preserving image processing or speech processing, they are brand new area. So they don't really have a regulation showing, okay, you should use visual learning or you should use differential privacy to protect those data. But the thing today is mainly talk about differential privacy is we want to look at the perturbation and the measurement. But meanwhile, there's a lot of effort on the visual learning community is also trying to do the same thing, but it's a little bit hard to measure the privacy loss with the system-based approach. But meanwhile, these things can be combined, but it's not today's talk, today's focus. All right, so before we talk about differential privacy, we want to figure out some exceeding efforts for our community. So when people coming from a security community or signal processing community, there always some shuffling or encoding technique for speech communication or secure communication, right? So for example, secure voice coding and compression, speech encryption or image encryption, decryption, and stringing matching, and the computational protocols. So those approaches do not provide privacy measurement, although there's really good encryption technique. And when we talk about this privacy measurement, that means we want to create a prediction model, and based on this measurement to see by setting a different budget or different privacy laws, how we affect our final performance of the prediction model. So when we look at this exceeding approach, they have a, for example, original data, original speech. They do some compression or encryption of the speech, and finally trying to recover speech from the original. But actually, the data coming from finite doesn't be. So even you do different encryption, the sample-wise information are the same. But meanwhile, there's other approach called the federated learning. So pretty recently, when we talk about those speech processing or this on-device technique, one thing is people don't really want to share the data on the central servers. So they empower a framework called the second pass rescoring for ASR, or second pass or decentralized model. That means when we have the feature or the data, those data and feature are separated and compute in different instances. For example, here is a classic example from the federated learning paper. So they call that horizontal federated learning. That means there is a data from part A and part B. They are isolated in different devices. But during the federated learning architectures, they will have a gradient aggregation progress to aggregate those information from each data, and then have the aggregate gradient for final updates. And then they will do the propagation through these aggregate gradients. So Google have an implement on their, I think it's the keyboard typing system. That means for each mobile device, they use Pixel as an example. So they will have this gradient information on each devices, but finally they will do the aggregation and use the aggregate gradient to update their central model, and then they will update their local devices. But federated learning and architecture have some issues. They have some good property. For example, it distributed the learning progress from central servers and end devices, and then avoid the direct access of those user data in model training. That means if my data is sensitive, my information will not directly be used by Amazon or Google. Maybe just some of my graded information or this non-direct information has been used. for example, the centralized, without this decentralized training, our information can be secured on this local device, but we don't really do a measurement, or we don't do a countable or numbers to see how much information actually sharing to the device, because it's just isolated. There are two different major field learning computing setups. That is for the introduction part, but it's not today's focus. I just go over that. The first part is this gradient aggregation, and the second is just trying to separate these feature structuring into devices. For example, you can see this part is a container and this is another. And they use the system approach to separate this information, and in this case, they can secure the data. All right, so there are some work, maybe from different approaches for speech, and you can do the same thing on image. The limitation is they don't have privacy measurement doing this data isolation, and they require additional system setup and cost. That means the latency will be an issue. Finally, the computing and the latency issue should be considered when we have a on-device processing framework. All right, so what is differential privacy mean? Well, so differential privacy is trying to perturb the data when we have these when we have two data, we're trying to protect the data coming from different instances. That means, for example, we have a distribution from data 1 and data 2. They are go through with the randomized algorithm A. So here is the randomized algorithm A. But we want this randomized, after this randomized algorithm, we couldn't figure out the data points from whether D1 or D2. That means how to measure my information as identical information is we using some randomized algorithm to let my data could not be distinguished with the average people or some random people on the database. So if this randomized algorithm is strong enough, the distance between this randomized D1 and D2, they will be much smaller. That means more privacy has been preserved. So that's the intuitive about differential privacy. Is want to measure how strong is the randomized algorithm to perturb this data, and then to that this information could not be distinguished. So if we are familiar with like divergence measurement, we can find out the distance between these two, like the probability density can be used to be measured by the range is divergent, and then as a special case, we can calculate scale divergence, and then we can have this distance bounded by E epsilon. And then in the long tail situation, we also consider this distribution have some shifting, which be bounded by the realization term, which is delta here. So I'm not sure how much you get it, but it's the big intuition of this differential privacy. I've kind of out today, I will have some mathematical discussion, but mainly you can think of if you want to measure and trying to have a numerical differential privacy measurement that depends on how strong your algorithm, and then use divergent measurement to see the distance. So again, we have the randomized mechanism. You can think that is applying some additive noise, and then they are domains. For example, they are coming from a speech data set. And from the database's definition, they will look at two adjacent input. That means all the pair input in the data set will satisfy this measurement. And like even they are different in one entry, they still could not be figured out by your perturbation from this randomized mechanism. And finally, there will be a range. Range means like a numerical range for the final prediction. So here, again, so if this distance between these two perturbed densities, probability density function, that means a small value means a strong privacy protection. So if this E epsilon becomes 0, That means you couldn't figure out whether it's your data or my data, and then your privacy has to be perfectly protected. So the differential means here is like the distance, and privacy means the identity. And here's the realization term we briefly talked about. So I'm sure you're not all from the mathematical background, so I use this framework to talk about. But like after these things, or if you are not understand this diagram, we can still talk about this after the talk. But for now, you can just take home message is like we want to use some algorithm to preserve privacy budget. And when the epsilon is a small number, that means more privacy has been protected from our randomized algorithm. Okay, that's it. All right, but the background of differential privacy has been introduced by database community, and the mechanism trying to satisfy when the mechanism of the epsilon delta differential privacy satisfy this inequality. So here is the original probability we looked at in the previous slide, and here is the distance based on the divergent measurement, and the last one, the delta is the realization term. That means the epsilon preserving a privacy represent the privacy preserving power of our randomized algorithm A that allow additional delta, which is the realization again. All right, so after this differential privacy has been introduced from database community in 2008, there's people trying to incorporate these things in the deep learning framework. So one challenge is when we talk about this randomized algorithm, people used to use shuffling or those kind of additive information on the databases themselves, but it's not directly associated with the gradient-based training framework. So one premier work is happening like showing the 2016. They call it Differential Private Stochastic Gradient Descent, DPSGD. That is the first successful theory that connects additive noise mechanism of differential privacy into learning progress to train neural network model. But one problem about this DPSGD you can think of, we have to use some randomized algorithm to add noise. But where we should add noise? For example, if we directly perturb the data profile, and then we use this noisy data to train a model, the model performance should be really worse because like you couldn't guarantee how much noise you should add. So their idea is trying to add a noise, doing the gradient updates, and then use some mechanism to update the gradient to avoid too much noise during the data training. But there's a problem become this DPSGD is the epsilon delta guarantee of DPSGD is not related to a performance of a deployed DNN model. For example, the DPSGD is first calculate the gradient of a loss function, and then add a noise. For example, we add a noise on the gradient, and then we have the like how strong the noise we should add depending on different differential privacy about the guarantee. And finally, we do the gradient update and the parameter update. But it's not directly related to how you design the model, how you design different neural network-based architecture. So how to incorporate deep differential privacy in the model updates and another layer of the interest when we really know, okay, there could be some connection between neural network-based training and the differential privacy. So our problem then becomes how to incorporate DP in the model updates. That means the original database training is trying to shuffle the data, but now we want to look at how we can use the data to train a model. And the things we really care about is the performance of our model instead of the identity in the database. So one of the more state-of-the-art model, they call the private aggregation of teacher ensembles. They call PATE, so it's a French term. So yeah, so the idea is trying to have ensemble learning progress when the random algorithm A depends on the stepwise update. So now we know to preserve our privacy, there should be some noise on the data. But there's a trade-off when we introduce noise on the data. But remember the basic of the machine learning. When you ensemble those models, those bias from the noise could be somehow eliminated. And then if we can somehow design a good mechanism to balance this noise declaration and model performance, we can have a good trade-off on the privacy we want to protect and the performance loss. So that's the basic idea of a private aggregation of teacher ensemble. So another theoretical finding is that the private aggregation of teacher ensemble have a privacy guarantee, which depends on the stepwise update. For the original DPSGD, the training update progress not depend on the state, which is T here. But in the PATE framework, we can guarantee this epsilon delta over T state of model learning. That means we can control our model and based on the model's update state to design our model independently. So we'll talk about PATE later. But meanwhile, I want to give some summary about the pretty recent approach about differential privacy. Well, the first time, the differential privacy, the epsilon delta differential privacy more specifically, so is proposed by Cynthia de work in 2019. The main property is they have a general bound, but data-dependent bound is not clear. The application is mainly on database statistics. And then furthermore, people trying to combine this database analysis to a prediction model like DPSGD. The main property is they connect differential privacy mechanism with the risk minimization progress, like people do this margin estimation during the SVN. But the applications mean like binary cost prediction. Finally, the DPSGD is people start to look at privacy as a thing behind the GDPR, and then we have the noise gradient updates. But the problem is they don't really have a data-dependent update, and the application in the DPSGD is ImageNet. And for PATE, like they further incorporate this property by this noisy aggregation. For example, we use aggregate mechanism. We teach ensemble learning, trying to eliminate this noise perturbation on our data, and then trying to maintain the privacy budget when the model trying to do not hurt the model performance so well, but we can further access the data-dependent bound. But the last part of the talk will investigate some PATE-based like ensemble learning for speech processing in our preliminary research published in the Interspeech last year. So that means for PATE, they associate with the relabeling progress. And then the paper we talked about last year is we trying to use a joint training generative model, trying to synthesize some fake data during this teacher student learning progress. All right, so yeah, during the time constraint, I have to skip some foundation about differential privacy, for example, how to divide this bound and how to get this epsilon delta definition. But I hope you get this measurement and how a randomized algorithm indicate a privacy budget. All right, so when we look at differential privacy and speech processing, how to equip a neural network-based speech processing model with differential privacy. So there is two perspectives we want to talk about. The first is we want to protect some specific speech data. For example, let's suppose some public data, for example, like the liberal speech TME, people use it for years. We suppose they don't associate with some severe identical information, personal information, personal data information. That means we can use teacher ensemble with knowledge digitalization. And so that is some of our recent work incorporated with Amazon, but I will not talk about this today. For today, we'll give a more general discussion saying we want to just to protect all the data. That means even the public data from TME and liberal speech, they associate with some sensitive information. Imagine you are a data provider of the ImageNet or liberal speech. So even though your data has been used by hundreds of thousands like computer science researcher or machine learning researcher, are you really feel comfortable or should people design an algorithm to protect your information? And the thing is, under those new data regulation, it is, and then we should give a measurable privacy budget in different conditions. That means we have to incorporate PATE with a generative model, and that means we have to try to synthesizing some data during the training. All right, so in the second scenario, we want to protect all the speech data under this DP production for training. That means design a new generative model jointly trained with the private ensemble speech model in work. For example, if you want to protect some of the sensitive data, like my data or some data from some people don't want to share to the public. We have the sensitive data. This data can be identity, gender, region, or ages. You can constrain something on the want to protect in the general DP framework. And then we use those data to train some teachers model. For example, isolated this data to several containers and to train a teacher's model. But meanwhile, we use a generative model, for example, a GAN or adversarial autoencoder. We're trying to train a data generator that can generate some fake data, but those data don't have this label information. And then if you are familiar with the teacher-student learning, there's a progress called the knowledge transformation. That means the teacher model will relabel your unlabeled data, and then you can constrain this unlabeled progress with the noise labeling. And then finally, we can add a noise on the ensemble output. For example, for each teacher's model, we add some noise trying to perturb this prediction from each teacher's model, and then trying to connect this noise to this differential privacy measurement. But finally, these things associated with ensemble progress. So this noise aggregation will not hurt the final prediction a lot. So, and then we can use this relabeled data to train a student model, and you can release this student model because these models are not directly trained on the sensitive data. And you can open this student model for the public, and you don't have to suffer in this inversion or the membership inference, because first, the data are not exactly exist, and the second is even they have been recovered, they are somehow the fake data. But another challenge is like how fake is your data, or how much data you preserve from this privacy perspective is we want to look at. So if we really look at the PATE-AAE architecture, is we try to use a discriminant network to model the latent space into a Gaussian distribution to generate sensitive data. That means for each time we have input data, and like the autoencoder training progress, we use encoder to have a latent vector, and then in the autoencoder we have decoder, and then to reconstruct the data as its input. In the adversarial autoencoder, we'll sample a distribution like a random vector from the Gaussian. And then for each time, we'll have a discriminator to find out whether the random vector is from the latent vector from your original autoencoder, or it is the real Gaussian. Like the game training progress, once they couldn't figure out whether it's a fake or the real, that means your latent space has been properly refined by the Gaussian distribution. And then you can directly feed in a Gaussian, a random vector simply from the Gaussian to a decoder, and then to generate your fake data. So after you have this synthesized data, we can train this student model, but the teacher's model will have this noise label, which under this epsilon delta constraint to relabel this fake data, and then finally we deliver this student model. All right, so that's the experiment setup. And if we really want to look at this architecture, it's basically similar to WaveNet. So we can have this, we can see there's a WaveNet cycle to generate this void, and then we have this random vector from the discriminator, and finally we have the output. Right, so I will not go into the detail, but feel free to ping me if you have further questions. And here is the adversarial autoencoded training progress. That means we use a random vector simply from the Gaussian to generate our score procedure eventually. All right, so there's some advantage compared with GAN, and yeah, let's skip it. All right, so this is the training progress of PATE-AAE. So we can look at for each teacher's model, they use the posterior, and then they have a teacher-student learning loss due to knowledge transformation. And finally, we aggregate this prediction from each teacher's model and then trying to jointly train your student model. So when we really look at the training progress, this discriminant loss and the prediction loss are training at the same time. And we still have the center cost entropy with the noise level for our final prediction on the student model. So there's some advantage of this training progress. That means you can further balance the differential probability loss before training the model, and then you can try to have a better performance with this ensemble. So we find out compared to a similar approach called the PATE-GAN, with different privacy budgets, the PATE-AAE have a better performance. I want to show that when people want to talk about this differential privacy budget, they usually use a budget between 1 and 10. But our approach, even in the really severe privacy condition, they can perform well compared to the standard approach. All right, and meanwhile, we're trying to measure this data quality by the Fletcher inception distance, and finally, they also have better quality. And we're trying to protect this data from the differential privacy perspective to against model inversion attack. So if you look at the first image, they actually model inversion directly from a well-trained speech model. So you can find out there's some spectrogram there. And without differential privacy based the noisy training, I mean, you can easily to recover those kind of acoustic features. But once these things have been protected with a different privacy budget, the attacker couldn't really recover those things, noisy training progress. But the things we want to balance here is the performance, and that's why we require using ensemble learning or the gradient-based methods doing this training. All right, so this is the first time we're showing, okay, this model inversion attack is possible on speech processing task, and incorporate differential privacy can empirically encounter this challenge. All right. So finally, there is some summary. So in general, even you get me of this mathematical or the design component, you can just have this takeaway showing privacy preserving machine learning is an emerging topic under this new data protection regulation. And indeed, we require more analysis on the accuracy, privacy, budget, and robustness. And there's a good paper published in Europe 2 years ago talking about the adversarial and the differential privacy, adversarial preservation of differential privacy. And people find out there's a trade-off, but depends on different conditions. Finally, there's a challenge between against differential privacy-based machine learning. Saying we use differential privacy as a general definition, saying all the database used here has been properly protected. But how much identity level information has been protected? For example, you want to measure how much like speaker information can be leaked out from a pre-trained model, or if a gender information can be leaked out from the pre-trained model. Does differential privacy really talk about this trade-off or really have this analysis should be further investigated? All right. And yeah, I want to advocate it. My advisor at Georgia Tech, so he is hosting PhD visiting students. So if you are a PhD student registered the Taiwan, the institute in Taiwan, and you want to work on robust speech processing and acoustic modeling for 3 or 12 months at Georgia Tech, feel free to contact me. So we don't have postdoc or PhD position currently at our group, but if you're a registered student at NTU or the other university at Taiwan, feel free to email me. And we are also recruiting some master student. If you submit admission at Georgia Tech next year, we'll give full scholarship for one student. Right. So I want to give some acknowledgement to my advisor, collaborator, and more. And yeah, feel free if you have any questions on both differential privacy, foundation application. I skipped a lot of math today, and there's some other talk is really separated from today's talk. So if you audience from previous talk, for example, causal inference, or content cycle learning, or the deep learning on the low resource data, you still have some questions, and feel free to contact me after the talk. And here's some publication, and thank you. Yeah, thanks. Yeah, feel free to ask questions.